So, welcome everyone. Good morning. For those joining early from Europe, we hope you're enjoying a fresh cup of coffee with us. And good evening or good afternoon to those tuning in from Australia, Japan, or elsewhere around the world. Thank you for joining us to celebrate the 40th anniversary of vanadium flow batteries. Since their introduction, vanadium flow batteries have made remarkable progress. Today, we'll explore a little bit of the history of this technology, from its origins and development to the major milestones that have shaped it over the past 4 decades. So who sparked the flow battery industry? What made it take off? How did it develop? And how has this technology evolved into a globally recognized energy storage solution, which has attracted lots of interest and support worldwide? In today's meeting, we'll talk to Professor Maria Skyllas-Kazacos from the University of New South Wales, Australia, followed by a brief discussion on the global vanadium supply and current vanadium flow battery projects. Before I introduce our guest speaker, may I please go over a few organisational details?
Mooie vergezichten op Lionhead, of wat was het? Mountain.
Could I kindly ask everyone to ensure they are muted?
Yeah.
Thank you. David, can we make sure everyone else is muted apart from the speaker, please? Thank you. You can submit questions in the Q&A section in Teams. We hope to have time for questions at the end of parts 1 and 2 of our webinar. And at that point, if you raise your hand, we'll unmute you so you can ask your question directly. But please keep order and watch what we're doing. And inevitably, we'll get asked at webinars if slides will be available. Of course, slides and a recording will be available after this event. So you don't need to worry about taking notes or taking screenshots. Just concentrate on what's going on, and we hope you enjoy this morning. So I'm delighted to warmly welcome Professor Maria. She's Emeritus Professor of Chemical Engineering at the University of New South Wales in Sydney, Australia. Professor Maria is a distinguished electrochemist, best known for her pioneering work in energy storage and really for her work in flow batteries. She's one of the original patentees of the all-vanadium redox flow battery, sometimes called VRFB or VFB, with more than 30 patents related to this revolutionary technology to her name. Her contributions have been essential in advancing the commercialization of VFBs, and her expertise is a cornerstone in building and standardizing the global flow battery value chain. Recognized internationally for her technical excellence, she's received numerous honors, including the Chemica Medal and the Kastner Medal. She's also a member of the Order of Australia and a Fellow of the Australian Academy of Technological Sciences and Engineering. Maria, good morning.
Good morning, Anthony.
Good morning. Right. Maria, let's start off. You were researching vanadium flow batteries at the University of New South Wales 40 years ago. Can you tell us about the development and how you realised that the vanadium flow battery idea could be a solution to the energy storage problem?
Well, it all started actually a little bit more than 40 years ago. 40 years is the anniversary of our first experiments at the university. But 2 years before that, the idea, the concept of the flow battery was introduced to me by a student who was one of our professional officers in the school. But this student was doing a master's with our highly acclaimed researcher Martin Green, who is the world expert in silicon solar cells. So Martin Green had visited Larry Thaler at NASA around that time, around early 1980s, and he became aware of the flow battery concept. And when he came back to Australia after his visit, he had one of his students, Bob Brand, start his master's thesis on that project. So when I arrived at the university in 1982, this particular gentleman, Bob Brand, he was our professional officer in the school, and I used to regularly bump into him in the laboratory where he was showing me the experiments that he had been setting up on the iron chromium flow battery. And during that time, we started discussing, and he had started to observe the major problem with the iron chromium flow battery, which was the diffusion of the chromium to the iron side and the iron to the chromium side, this cross-contamination. And during the discussions, it became obvious that this is something that couldn't be avoided because no membrane has 100% efficiency. So in order to avoid it, I was also fortunate to have another colleague in the school, Professor Bob Robbins, who was an expert on vanadium chemistry. He was at the time studying the extraction of vanadium. He'd been doing some work with some local vanadium companies back then. And during those discussions, it's sort of the concept of using vanadium, because of all the 4 different oxidation states that vanadium can be found in solution. Having looked at the literature at the time, it didn't really look that promising because the literature suggested that the solubility of vanadium-5 is extremely limited. And we all know that flow batteries have to have a high concentration of the active species in solution. Also, the reversibility of the vanadium redox couples did not look very promising either. And also vanadium at the time was regarded as being relatively expensive. So the solubility, the poor reversibility. So at the time, it didn't look very promising, but we thought, okay, we're going to give it a try anyway. So that in 1984, I had a student, Elaine Sum, who's pictured there in the photograph, in that middle photograph, in that center image. She applied to do her honours thesis with me. And I was very fortunate because she was our star student. She was in line to receive a university medal. So at the time I thought, oh, gee, I was feeling quite nervous having her doing the project. I was very anxious. I wanted to make sure that she was going to get some good results and that the project wouldn't be a dud. So during the Christmas holidays, I got some vanadium solutions, made up some fairly dilute solutions, and then just did some really rough experiments. And I found, oh, okay, I can see some cyclic voltammetric peaks. So I thought, okay, it looks okay. I'm going to put her onto this project. So she started that year. And during the course of her research, we started to identify the same issues that were reported in the literature, that the reversibility wasn't, in fact, very good. But every time she would do her cyclic voltammograms, she wouldn't see any reversible peaks. And yet I had already seen it during the vacation time that you could see it. But and after going backwards and forwards in the laboratory several times, it became obvious that when she was doing her cyclic voltammograms, she was doing it very methodically, meticulously polishing the glassy carbon electrode, whereas when I had been doing it, I was just scratching the electrode and putting it into the solution. And then it sort of clicked that obviously in order to get any reversibility, we need defects on the surface of the carbon because they produce the active sites where the reactions happen. So that, I suppose, was one major breakthrough in identifying that potentially vanadium redox couples could be promising. So she continued on during her thesis in 1984, and she studied a whole range of different supporting electrolytes, different conditions, tried to find out the maximum solubility for the vanadium pentoxide, for example, and other oxidation states. And we got 2 papers out of her thesis, which was amazing. And in fact, those 2 papers have been cited hundreds and hundreds of times. And during her research as well, we didn't have a proper cell, so we just got 2 glass compartments separated by a porous glass frit, and put the 2 solutions in there and ran it as a stationary cell. And we got some performance, some charging and discharging out of it. But at the end of that project, we decided to, I contacted my colleague, Martin Green, and we thought, well, let's apply for a grant. At the time, we were very fortunate. The Australian government was providing funding for renewable energy. but also for remote area power systems, because Australia is a vast continent and we have many remote communities which are not connected to the grid. So the government had one of the priority areas for the research projects, for the research grants, was new systems for remote area power energy storage. So we applied for the grant, and together with my colleague Bob Robbins and Martin Green and Tony Fain, who was our school's expert and an international expert in membranes, we put together an application and we were successful, especially since we had some results from Elaine's thesis as well. So that led us then to allowed us to employ more people, to continue working on the project. Dr. Miron Richik joined our team for a few years, and he was very, the work that he did was also very important, very, very critical. We then had 2 master's students joining the team, and that included my husband, Michael, which interestingly, because at the time he was working for the Department of Health in their analytical laboratories. And when he saw this work that we were doing, he became extremely excited. So he decided to change from being an analytical chemist, and he applied to do a master's at the university in energy storage. And so he joined our group as a master's student under the supervision of Tony Fain, our membrane person, and also Franz Grossmith, who looked at the design and tried to build a proper flow cell so we could get reasonable performance. And then shortly after, we were able to publish our first paper on the all vanadium redox flow battery, which appeared in the Journal of Electrochemical Society. And these are just some images showing the first all vanadium flow cell, which was fabricated in 1986. And then very quickly after that, having more members of the team, we were able to look at other critical parameters that we had to address. For example, solubility, because one of the things that Elaine found was the vanadium pentoxide was extremely insoluble, and she could only get about 0.3 molar solutions for testing, which was obviously way too low for any practical use. So we realized that if we started off with a more soluble form, like vanadol sulfate, to our surprise, we were able to make a 2 molar vanadol sulfate solution. And when we charged it up or oxidized it to V5, it didn't precipitate at room temperature. So we showed that we could actually make a 2 molar solution. So we're able to solve that problem as well. But very soon after we started working on that, we became we were very fortunate that we started to attract quite a lot of commercial interest, because the university published a small article in our university newspaper at the time, and it was picked up by the newspapers and television, and we were on the news and everything like that, which was sort of very surprising at the time, because we only had a very small cell with very preliminary experiments. But that led to a company in Western Australia called Gary Agnew from Agnew Clough Limited in Western Australia. He became very interested because they had a vanadium resource. They could see that the vanadium, their resource could be used in a future large-scale energy storage device. So they approached the university and applied for a license, and they were granted an exclusive license at the time. But very quickly, the first thing he said to me was, "Maria, if you're using vanadol sulfate, that costs $800 a kilo, for high purity vanadol sulfate. Forget it." He said, "I'm going to send you a barrel of vanadium pentoxide, and you've got to find out how you're going to put that into solution so that you can start off with a more practical, commercially viable raw material." So within a week, he sent us a big barrel of vanadium pentoxide, and we're thinking, okay, now how do we put it into solution and get it to dissolve, because vanadium pentoxide doesn't dissolve easily. So our colleague Rod McDermott, who's also seen in this photograph on the right-hand side, he was a very practical, hands-on person. So one day he got some samples of the V2O5 and he put it into a beaker with sulfuric acid in it. He stirred it with a magnetic stirrer, put 2 electrodes in there, passed a current, And within about an hour, he came running to me, said, Maria, it dissolves, it dissolves. So all of a sudden we thought, okay, this can be practical because we can use a cheap raw material. We don't have to use this very, very expensive starting material. And then that led us to look at other, because when you do that, that process only allows you to produce V4, because the vanadium pentoxide suspended powder electrolysis is reduced at the negative electrode, but then it reoxidizes at the positive electrode. So you can only get a V4 solution. But very quickly we're able to extend the process conditions and put in a membrane and did all sorts of different things. We looked at chemical reduction to get it into solution. We looked at electrochemical reduction and even leaching of using V3 and regenerating the V3 electrochemically. So that allowed us to file a patent very early on the electrolyte production. And so after that, we started looking at also looking at membranes, trying to identify commercial membranes off the shelf that we could adapt for the vanadium battery, because suitable membranes didn't really exist back then. So we did a lot of screening of membranes, electrode materials, graphite felts, the electrolyte, optimizing the electrolyte, and then started looking at designing and scaling it up, because up till then we were making small cells. But then we brought in some mechanical engineers and we thought we're going to scale it straight up to, we were getting 90% energy efficiency at 20 milliamps per square centimeter in our small cells. But we thought, okay, let's scale it up. And we went straight to a 1 kilowatt. And to our surprise, we were getting the same efficiencies in the 1 kilowatt battery as well. So that was very exciting for us. So from there on, we just kept on looking at improving the designs, looking at new materials. And we kept going from there. Sorry, I can't hear you. I can't hear you, Anthony.
Maria, that's a great story. It's really interesting to hear how many people you had to bring together. But one of the things which we often hear about is the difficulty of getting funding for new ideas. You obviously had a little bit of a success with the Australian government funding, but how easy was it for you to persuade other people that this was a venture worth following and they should invest in it?
Surprisingly, back in those days, it was relatively straightforward. We didn't have too much trouble getting funding in the early days. The government had a few really good funding programs. I mean, compared to the money that people and or groups get these days, we were getting fairly small. It was a pittance what we were getting, really, but it was still allowed us to employ a few people. And, one of the things that Michael had to do is to want to go around and scrounge things for free and bring up people and getting free samples of things, just so that to stretch our budget as much as possible. But we were able to get some funding, and because of the early license that we got through Agnew Clough Limited, that they also funded us for a few years with additional funding, and that allowed us to do a lot more additional work. For example, developing and conducting plastic electrodes, and we started doing some of the modelling back then as well. And we were continuing. Then New South Wales Department of Minerals and Energy became very interested in the project as well, and they provided additional funding. And we were able to get reasonable funding, leading to the commercialization. We were able to get two other. First of all, even the university had actually exclusively licensed the technology to Agnew Clough in 1987. But because of there was a financial crisis in Asia at the time, and a few years later, and because of financial problems, Agnew Clough wasn't able to continue funding and financing the project. So they returned the license to the university. So at that point, the university was able to find other licensees. And because of the ongoing, I suppose, media interests, we were getting people from all over the world. In fact, we had Reuters putting an article in one of the Thai newspapers and all over the place. So a company called Thai Gypsum from Thailand became interested in the technology, and they approached the university to negotiate a license back in the it was actually 1992, around that time, for the Southeast Asian region. So they provided some funding, because one of the things that they wanted to do is have us build a battery, send it to them in Thailand, where they could install it in this solar demonstration house that they were building on the site of their new factory. And they wanted to be able to showcase this new concept of having a solar house with a battery to store energy. So that gave us a little bit of extra funding. And so what we did, we built the battery at the university, we sent it over, we made the electrolyte. Because we needed quite a large volume of electrolyte, we in fact even built a pilot plant for producing the electrolyte. We could make about 1 cubic meter of this electrolyte over a couple of days. So we built a pilot plant, and we made the electrolyte, shipped it across to Thailand, sent a couple of our research group over there. One of the things that we had to also do, because it was it was integrated to a solar house, and when we were looking at the load profile for the solar house, we realized that if we were running the battery all the time using the load profile for the house, and if the pumps were running all the time, they would consume most of the energy, because at night time you don't use many appliances, and the battery might only be drawing a couple of amps, and if you're running the pumps under those conditions, most of the energy goes into the pumps. So we were working with one of our colleagues from photovoltaics who developed a simple on-off controller, where it was designed so that when the current coming out of the battery was greater than 20 amps, the pumps would switch on, would turn on, would run continuously. If the current was less than 20 amps, the pumps would switch on and off intermittently, monitoring the stack voltage. When the stack voltage dropped below a certain point, the pumps would switch on for 3 minutes, flush the solution out, and then switch off again. And that way we were able to get some really good efficiencies with minimal pumping energy losses. So that was very exciting to put that, to implement that project. And then, sorry?
Yeah, I was going to say that sort of leads me on to my next question. This is great for having interest from people, and you've got some early licenses, but who were the first commercial users? So taking this away from just demonstration and getting into
I suppose
applications.
Well, it depends on whether you regard Kashima Electric Power Corporation. They were really doing a field trial, but they had been working on the iron chromium flow battery at Kashima for a few years before switching across to vanadium, and then they licensed it from the university as well. And for 5 years we worked together with them, which led to the first 800 kilowatt hour vanadium battery that was installed for load leveling purposes at the Kashima power station in Japan. So you could sort of say it's semi-commercial, but it wasn't fully commercial. It was still a field trial. But then after that, the university sold the patents. And because at that point, that's when we started really struggling to get funding, because we had reached a point where everyone regarded the technology as ready to go to market. So therefore, a lot of the funding which was really available was for research. So there was really, then that's where we identified a major gap for commercialization of new technologies. You could get a lot of funding from the government to do early research, but then until you had some commercial partner who was going to put in a lot of additional funding to scale it up and take it to the market, there was just nothing in between for funding. And that's why at that point in time, the university, was sort of quite desperate, and we couldn't get any funding anymore, because unfortunately, we had a lot of companies in Australia that we had approached back then, but most of the Australian companies, they're either construction or they're mining companies. They wanted 2 or 3 year payback period. They couldn't see a payback period of that short duration for such a technology. So we just couldn't get any funding. So the university sold the patents. We were approached by a Western Australian company that saw the potential. But unfortunately at the time we thought, oh, fantastic, this is going to continue funding our work. But unfortunately that didn't happen, because being a listed company, there were so many takeover actions taking place all the time from all over the place. The company was always under takeover threat. So, and in the end, they were taken over, and our patents then ended up in Canada, VRB Power in Canada, and then during the global financial crisis, all the assets of VRB Power were purchased by Prudent Energy. And it was only probably a few years after that we started to see real commercial application. And in fact, in 2006, when the first patent expired, we had other patents, but they weren't the critical ones. When the first patent expired, then we could see a lot more activity. Companies were able to develop and explore the commercialization without any freedom to operate issues. So that's when we started seeing the early 2000s, some of the first commercial systems going up in Japan, in China, CellCube in Austria, projects in California and so on. So yeah, so it took some time, but even then, the market was still not fully developed. Companies were still probably struggling to get enough orders to keep them going, and we saw so many companies coming and going, unfortunately.
Yeah. So if we cast our mind back to those days, in the beginning you were talking about the Thai solar house, but PV generally was a bit of a curiosity. Even wind power was relatively new, and I can remember in the early 1990s, the oddity of going to California and seeing a few people fresh out of university just putting a wind turbine up to see how it would work. And we compare that to where we are with the renewable industry now. My recollection is back in the 80s and 90s, it was all about trying to provide peaking power and making best use of low-cost base load from either heavy coal, nuclear, or hydro, and a little bit of frequency control at the upper end. We compare that to today's power systems, and the whole market has completely changed. So
almost overnight, Anthony, almost overnight.
Yeah. So, but that really should mean that we've come out of flow batteries, and indeed just generally battery energy storage being a curiosity, being something that people talked about in darkened rooms at night for fear of being accused of being living in fantasy land, to something which everyone now wants to get into. So how would you describe the status of the flow battery industry today, Maria?
Well, I think all over the world, people now are scrambling to try and see how they are going to meet their decarbonisation targets. And it's only probably in the last 2 or 3 years that Australia's taken it quite seriously. So, as people are starting to think ahead, how they're going to decarbonise, they realise that we've got to put in a lot more solar and wind, and we're not going to be able to decarbonise beyond a certain percentage of renewables unless we've got storage. And the more that we decarbonise, the more storage we need. And that's why 6 to 8 hours or even more is going to be critical. This long duration energy storage is now starting to emerge as a critical component of technology in order to be able to achieve our net zero targets in the future. So,
okay. Yeah, all right. Okay, so you talked here about several projects outside Europe. Using my prerogative as moderator, I'd like to emphasise that there are many exciting developments taking place here in Europe, and thank you very much for coming to speak to Flow Batteries Europe. So if we go on to I'll look at this now slide, this shows the selection of some of the many flow battery projects in Europe. There are many more, and we're currently working on a map of flow battery projects, which we hope to add to our website. We've also got a growing representation of companies across the flow battery industry, which includes more than just vanadium flow batteries. Last year, flow batteries were included in the batteries regulation, a new EU law that covers the entire battery life cycle from production to reuse and recycling. While this introduces many new compliance requirements for the flow battery industry, it also supports further development of our technology. we've got a few moments now before our next speaker. Do we have any questions for Maria? I think David Hodgson was putting up his hand.
Yeah, thanks, Anthony. Maria, Dave Hodgson here. We've met a few times, and congratulations on achieving this milestone. It really is significant.
Thank you, David. Thank you.
You should be super proud, I think, of being able to see this legacy that's rolling out in front of you. Just on that point that Anthony's kind of just touched on, though, obviously you identified early on that there were some challenges with existing flow battery chemistries, which led you to that genesis of vanadium concept. I mean, since then, there's almost been a kind of mini explosion of alternative chemistries. Where do you think vanadium stacks up against those right now, and which ones do you think are particularly exciting in terms of delivering ultimate value onto the grid?
Well, I think the vanadium technology is much more advanced than a lot of the other flow cell chemistries at the moment. So I think for a few more years, it will probably dominate. Here in Australia, there's a lot of interest now and activity relating to the iron flow battery, the all iron, the ESS technology that's been. We have an ESI entity here in Queensland that is managing to get quite a lot of government funding, both state and federal funding, to develop and to bring the iron flow battery into Australia. And there's a big test program at the moment with the Queensland University of Technology, and they're looking to set up a factory to manufacture it. But I think, at the moment it's still really semi R&D, because there's a lot of problems that still need to be solved in order to get high efficiencies, and the long-term durability, the long-term efficiency and performance is yet to be really proven. And that's the thing. Fortunately, vanadium batteries have got a long history now. We've got companies that have been running these things for more than 10 years and getting consistent long-term performance. And so vanadium companies can say, yes, it will last for a certain number of years. It will undergo that many thousands of cycles. The other chemistries have yet to show that. They are promising, 25 years, but we haven't seen it yet. So there's the iron flow battery. We also have this company here in Australia called Allegro, and they're developing a micro-emulsion battery. And they managed to get some good funding from one of our power suppliers, power companies, and they're looking to actually launch one of the first product of a few hundred kilowatt hours in the coming months, using vanadium battery infrastructure and just putting in their electrolyte, which is fortuitous, and that's the great thing about flow batteries, because it seems that a lot of the flow cells, all the infrastructure, the hardware is applicable it can be interchanged. The chemistry can be interchanged. So that allows all these new chemistries to actually now take advantage of everything that's gone before them through the vanadium battery development, so they can fast track and hopefully get products to the market. And I think in the end, we are going to need more than just vanadium, because, if the demand is going to continue, yeah. But at the moment, we've been working with Rio Tinto, and they've sort of identified for now, the vanadium seems to be the winner as far as they're concerned for now. But of course, we don't know what's going to happen in the coming years.
Okay, thank you. I think Terry Perez has got his hand up. Is Terry there? No? Okay. And there's one quick question from Satish.
Sorry, Anthony, I'm here.
Oh, Terry's in. Come on, Terry. We just time.
Yeah, sorry, my camera's not working too well here yet. Maria,
Hello,
nice to
Terry.
see you. I think. How are you? I think maybe. Sorry, my camera's not working, but
I can hear your voice.
Okay, great. I think we probably first met around 1990, so I've been following this not quite as long as you have, but it's really interesting, the developments that are occurring now in this space. When we talk about vanadium, one of the points I'd like to make is that we've got, in terms of resources in the ground, there's probably 150 years worth of vanadium in the ground. And the vanadium industry has been remarkably resilient in terms of being able to expand capacity as demand has expanded. The one concern I have is as we look at this, particularly from an EU standpoint, EU is a net importer of vanadium, and a very significant amount of the vanadium produced in EU today is processing Russian slag, and that slag will be removed from the market come January of next year. So as we see the growth in opportunities for vanadium batteries in EU, we have to think about the security of supply of vanadium from the EU specifically.
So, Terry, that's an interesting point. Maria, can we'll just hold that for a second, because I think probably we ought to go straight on to our next guest speaker, and we'll perhaps come to pick this one up with you, Maria, in 10 minutes' time. Our next speaker is Jana Plananska, who works on the board of advisors at Norge Mining. Jana, you just heard a comment from Terry about vanadium supply. We look at the next briefing slide we've got. We hear from Human Zhang. Can you put the next slide up, please, David? But if we are to meet the targets for energy storage, with more than 100 gigawatts of storage coming onto the market, we will need a phenomenal amount of storage capacity. And if we use that with VFBs, we need enough electrolyte to run 180 gigawatt hours, which I believe works out at being 1.5 million tons. Jana, how are things progressing for Norge Mining, and when can we expect mining operations to begin in Europe?
Yeah, hello everyone. Thanks, Anthony, for the question and for having me. And yeah, thanks, Maria, for the great history of the flow batteries, fascinating story of new inventions. And yeah, so there was a very good point from Terry. And in general, that's kind of the situation where we are standing right now. The demand for vanadium as part of the flow batteries is expected to grow. As Maria has pointed out, even looking at the market developments, vanadium flow batteries will still keep dominance in the market. And it is expected that even by 2050, just the demand for vanadium in flow batteries will be as big as the market for vanadium as such in 2018. And now, as Terry was also pointing out, almost 80% of the global supply comes from Russia and China. Europe is 100% import dependent on vanadium feedstock that is then being processed, but exactly this feedstock is coming from Russia. So to fulfill this demand, to be able to supply the growing demand, supply of vanadium has to grow, and there are enough resources globally. That's the good news. The question is, however, that they need to be explored and processed under the high standards, which is of course coming with increased costs, financial, environmental, and also considerations for the politics. So there are new projects in Europe now being under development. One of them is Norge Mining, which is Anglo-Norwegian mineral company with world-class resources of phosphate, vanadium, and titanium in southwest of Norway. We are working on our operation since 2018. Right now, this summer, we have successfully concluded pre-feasibility study. So we are on target and progressing to our schedule to start producing magnetite concentrate as part together with other products. But magnetite concentrate that is a precursor for vanadium oxides by 2029. But of course, this is not coming easy to develop a new project in Europe, and even more like there is much more happening on the EU level. For example, we see positive political developments on the EU level, such as the CRM Act or the other regulations, the battery one you were also mentioning. But more funding and more support is needed to really get these projects on the ground. But we believe that we can make a substantial contribution to that in the future.
Thank you very much, Jana. We'll come back to you with some more questions in a moment. We've invited our next speaker to talk about a real-time example of a vanadium flow battery in operation. So Dr. Thomas Luth from CellCube, is going to talk to us. CellCube's been in the flow battery market for many years. Thomas has had more than 2 decades of experience on flow battery systems for large-scale grid and off-grid applications. Thomas, what's new at CellCube and what project are you going to talk to us about? And we've got about 5 minutes for this, not much longer, please.
Yeah, there's a lot of news from CellCube, and thank you for inviting me to speak today. I have one project selected that I like to highlight a little bit because it combines a lot of the history that we have. And basically that's located in the Rocky Mountains in Bridgeport. That's Momo County, very close to Nevada. It's a high altitude project on a military base, and you see now there's basically 4 batteries that we will install over there, and they have 2 will be installed early next year and 2 a little bit later, so that's why they look a little bit different. And the interesting thing is, please go to the next slide, that the application on this base, that's a military base, a marine base in Momo County, as I mentioned. And this is very high altitude, so it's above 2,000 meters, and they have a very weak grid. So they usually rely a lot on diesel fuel that they need to truck in, and during winter time there's a lot of snow, and then they cannot truck in diesel fuel. So they're expanding their renewable integration. They already have some solar over there, but this is a typical case. What we recently see, that we have a way more island grids, more microgrids that try to decarbonize. We see this in military bases, we see this in mining, we see this on islands in general. We see this in remote towns in northern Canada. All of them try to decarbonize, and usually we have they have all more or less the same operation modes. We have a normal operation where we have likely weak grid connection. We have somehow then disconnected, or the sites are disconnected in the grid because of wildfires or stuff like that. And we have then islanding periods, and this can be between very short and very long. And of course, then the battery needs to serve in a different way, and everything needs to be optimized. And you can imagine that the Department of Defense is a little bit a critical customer. So they really like to get a proven technology, and so we need to build trust. And on the next slide, what we then usually do is we invite them over and come to our facility. So in the upper left picture, you see one of our units just sitting on our site and is working. So it's working. You can visit us and you will see that. And the left lower picture, that's our shop where we assemble the units. And but they, in most cases, they not only take our word for granted, they like to talk to other customers. And the right picture, you see the folks from the DoD, together with a few people from us, and with a customer in California, that's Applied Medical, which has already deployed at 2 different sites our batteries, and they will deploy more of those batteries. And this then is usually a good story and convince the people. So as Maria mentioned, CellCube is already in the market for over 20 years. And our oldest battery is operational since 2010, and it's still operational, and it still shows the same efficiency and the same power and the same energy rating compared to the very first day. And I think this is something that is great. I was told only to give a few words on a project. We see a lot more projects coming up. We have already on the IFBF, I mentioned that we have a clear trend towards longer duration, and this continues. All of our recently signed projects are typically 8-hour projects.
Super. Thomas, thank you very much. And if we can just get Maria and Jana back with us again. One question, Thomas, you just said that your projects are often 8 hours. Is there a reason why 8 hours has been chosen? And this is open for you or for Maria or anyone to answer. What is the optimum duration for battery storage?
So we do see applications in 4 hours as well, but there's always a lot of competition with lithium, and but at the moment we see a sweet spot in the technology from 6 to maybe 12 or 16 hours, and that's what we hear from the market as well, and that's for vanadium. And of course, if you go with we see a tendency that even longer duration are asked for.
Okay. Maria, have you any comment on storage duration? Because that is often cited as one of the really attractive features of a flow battery.
Yes, I think in the short term, definitely we need for long duration energy storage, 8 hours is the minimum that is going to be needed. But as we go for greater penetration of renewables and reducing carbon, then that's going to increase definitely. We've been working with Rio Tinto to do quite a bit of modelling for some of their operations in the Pilbara area, and some of the early modelling is definitely confirming that the 8 hours is good for their, if they want to decarbonize by 50%, 8 hours. If they want to go beyond that, it's going to be a lot more than 8 hours, definitely. Okay. But of course, one of the issues that we have is with if you go fully renewables and storage, as we know, there's always that a few percent of the demand was going to need a much larger capacity that is probably economically feasible. And do you go to 24 hours, because that becomes very expensive, just for a few percent of your requirement over a 12-month period, for example, and you've got a few continuous days of rain or cloud and no wind. And that's where I think it's a little bit tricky to determine whether or not that will be achieved by increasing the capacity of the flow battery or having some other generation capability, such as natural gas in the short term, for example, to meet that small capacity demand. Okay. So would you agree with that, Thomas? Is that...
Yeah, absolutely. Just last week I had some talks with a big power company and a utility, and they say if we're going for 95% renewables, that's pretty easy. But to cover the last 5%, this is tremendously expensive. And so I totally agree that there will be still some thermal plants or something like that, or maybe hydrogen too.
Yes, or hydrogen or natural gas in the short term.
Okay, thank you very much. We have time for a few questions. There have been a few hands going up. Satish, you had your hand up first. Are you there, please, Satish Patel?
Yes. Okay. Hi. Yeah, Maria. So congratulations. I think it's a fantastic work on vanadium flow battery. There are other chemistries are evolving. For example, in India, we are working on soluble lead redox flow battery. So there is no membrane. I think one of the major advantages it's a membraneless flow battery. It's very cost effective, but however it contains lead. Do you think it's a concern going forward to commercialize batteries which contains lead as a major?
Well, component? I think that's because lead has been an environmental issue and a health issue for quite a long time already, and having such large volumes of solution with lead, it's even worse, isn't it, than having solid lead batteries. So this is going to be an issue. It's a health and safety, health and environmental issue, I think.
Okay. Thank you very much. Let's move on. Virginia, you had your hand up, please. Can we find Virginia? No, we can't. Okay. And Antonio had his hand up. we find Antonio? No, we can't. So Terry, you've come back again with a hand. Is that an original or
Yeah.
a
Do you hear
subsequent
me?
question? Sorry,
Yes, the question is related to the break-even between lithium and vanadium. We expected in the past being around 4-5 hours, then 6, then we are measuring that at 8 hours, but lithium is still more competitive. The question is, do you think that the break-even in this moment is around 10 hours? Let us speak about 10 megawatt, 100 megawatt hour. This is the range of power and energy.
So, Antonio, I just wanted to say that a lot of these calculations are all dependent on what the vanadium price is when you're doing your techno-economic modeling. So if the vanadium price goes up, it's going to be worse. If the vanadium price comes down, it's going to be much shorter. If you factor in the possibility of leasing, that would make it even better. The electrolyte leasing has been discussed already, and potentially could become an important mechanism in the future. But also, we expect at the moment, vanadium flow batteries are made by hand, with very little automation. And so we haven't even started to see the effect of automatic assembly and automation on the cost and as we scale up production. And this is where we're sort of pushing at the moment. We already see in China, Rongqi Power has already started introducing robotic systems which are assembling battery stacks. ESS has built in the US for the iron battery. They've already got almost fully automated assembly line. So as we see more and more automation be implemented for flow batteries, the cost of flow batteries is going to come down dramatically. But of course, in order to get the vanadium price to come down as well, we've got to start producing more vanadium, and that's one of the big priorities, I think, for the vanadium industry, how we can make sure that we can facilitate the scaling up of the vanadium production around the world.
Jana, do you have any comments to add to that?
I can just agree, right, that currently the huge price fluctuations of the vanadium are not conducive to the growth of the sector, right? Because the market is very small, very concentrated. So every small impact on every single producer can have massive impacts on the prices, as we have seen even in 2015, bankruptcy of one company then led to massive growth of prices. Last year, vanadium prices went down and had a further impact on the industry. So only with more supply and from more reliable countries and more stable partners, this can stabilize so that it would have even a more positive impact on the whole market, right? So can only agree.
Okay, a question for Thomas then. And this, if we had more time and it was a more open session, we would address this to every flow battery manufacturer. What are you guys doing to improve the efficiency of manufacturing and flow batteries, getting the cost down, really getting into the market and meeting that huge demand that there is for energy storage?
Yeah, I think besides automation, the design for manufacturing is very important. We need to design the batteries in a way that they are easy and fast to manufacture and to deploy, so that so manufacturing the battery is one part of the cost, but deploying it and do a lot of field assembly and wiring is costly as well. So all the cell cube products that have been designed lately are really designed for manufacturing and designed for easy deployment. And of course, we're always streamlining our production process. We put in automation and robotics here and there, but slowly, so that we gain more about or we save more time in optimization of our processes.
Okay. So are there any more questions going up? Virginia, we did see your hand go up, but it came down again. No.
Maybe I comment on the break-even point of 10 hours or as well. So we as CellCube, we don't see a clear break-even point at a certain hour. So of course, it's dependent on the vanadium price, but also on the application. So we see a lot of applications that do more than one cycle a day, which is obviously not possible with 8 hours. But we see some applications where 4 hours meet the customer requirements very well because they know that they will cycle twice a day, and so they abuse lithium, or they know that they have very high ambient temperatures, so they prefer to use a vanadium flow battery because it's more efficient in this region. So that's not only about storage duration, it's a bunch of factors that go into these calculations.
Okay, thank you. Terry, is your hand still up?
Yeah, it is. Really quickly, on the issue of cost, there's two parameters, of course, the physical plant and the vanadium. And we don't have gigafactories for vanadium flow batteries in place today. I've spoken with flow battery companies that think they can reduce the cost of the physical plant by about 70% as they get up to scale. Obviously, that takes capital, and that's the challenge for that industry. You mentioned vanadium, and of course, it's notoriously unstable in terms of pricing. Maria mentioned, I think, the leasing model, which is very interesting given the fact that the vanadium electrolyte can be cycled an infinite number of times. And when you look at it from that standpoint, the cost per cycle starts to approach zero. So vanadium is very important in terms of cost. I don't know what price Rio Tinto has baked into their calculations, but a week or so ago, they made a presentation discussing vanadium flow batteries in their mining operations. And they have suggested that beyond 4 hours, the cost of the vanadium system is lower. It's much more economical. And interestingly enough, they're suggesting that there are applications in their mining operations that will require durations of 48 hours. So as we go out to longer and longer durations, the advantages of the vanadium system really start to shine.
That's super. Okay, thank you. We've just got 2 minutes left to go, so I think I'm now going to hand over to Beata to talk to us about Flow Batteries Europe.
Yes. Hello, everyone. Thank you, Anthony. So I just wanted to mention a few words about Flow Batteries Europe. We are members-led association based in Brussels, and currently we have 30 members, primarily based in Europe, but also companies entering European market and interested in EU policy developments. And our main activities involve shaping the legal framework for flow batteries and contributing to EU decision-making process. We do this by raising key questions and engaging with politicians here in Brussels. It is important for us that all our members are informed about how new regulations may influence their businesses, and we ensure that voice of flow batteries is heard here in Europe. Currently, we are working on quite some projects, but one of the biggest, which we are about to start, is a working group on carbon footprint calculations rules for flow batteries. As you may know, as of 2030, every flow battery put on the European market will need to have carbon footprint declaration, indicating also how this was calculated, but there are no rules. And we want to gather industry representatives together, decide what is the best approach, agree on how these rules should look like, and then propose these rules for European Commission. that's what we are working now on, but we also together discuss such topics like battery passport, recycling of flow batteries, performance and durability, PFAS chemicals used in flow batteries. All this seems to be technical topics, but many of them I decided and written down in regulations. So we want to ensure that politicians understand also our technology and everything goes in line with what we can bring, what solution flow batteries can bring for green transition. If you want to know more about any of these topics or about our activities, please contact us. Here's contacts of my contacts as policy officer and Anthony's contact, who is Secretary General of our association.
Thank you very much, Beata. So thank you all for joining us today. We've had a wonderful session exploring the advancements, challenges, and looking at the future potential of vanadium flow batteries. My special thanks to our speakers, to Maria. You've made this whole webinar possible, not least because you started this journey 40 years ago. And it's been great to help you celebrate your anniversary of the starting the research in at UNSW. So thank you too for Thomas and Jana for sharing your insights and expertise. Your contributions have made this webinar really useful. So please also, I note our thanks to all our attendees. We had over 300 people register for the conference, many of whom managed to have joined us this morning. I do see that some people have suffered from the same pitfalls that I have and end up joining conferences an hour late because of changes from one time zone to another. So our commiserations to them. But this webinar will be available on a recording, so look out for an email from us in due course. Keep an eye out for our communications. Sign up for our mailing list if you want to be kept in touch. And if you've not had your question answered today, please send it in to Beata and we'll try and get some answers back to you. Thank you again. Keep in touch, and wherever you are in the world, please look after yourself, keep safe, and we hope to see you soon. Thank you all very much. Goodbye.
Thank you, everyone. Bye.
Bye.
Bye-bye.